This webinar will examine eigenpairs, eigenvalue, eigenvector pairs. Now, clearly Maple can find eigenpairs, but we want to show how Maple brings simplicity to the calculations and enlightenment to the conceptualization of just what are these eigenvalues and eigenvectors. To begin, we want to attach the discussion to something that is a little bit more concrete and perhaps already known. We want to consider fixed points of a function. So a fixed point for a function f of x would be the solution of the equation f of x equals x. And here's an example. The function is x squared minus 3x minus 12. And we set that equal to x. So we have this equation here, which becomes this quadratic here. And the left side then factors as shown. And so the solutions are x equals -2 and 6. And if we look here at the graph, this is a graph of f of x. And the line y equals x. And where these two intersect are the two solutions that we see here, fixed points. So the question about eigenvalues and eigenvectors can be phrased as, what can a matrix leave fixed? This would be the fixed point statement, ax equals x. So you multiply x by a represents a linear transformation. It returns x. Well, here is a matrix A, and here is a vector x, for which ax equals x. So it is possible for a matrix to leave a vector fixed. Now, a vector is thought of as something that, an object that has length and direction. Okay, so here I'm asking the question, can a matrix leave the norm of the vector fixed? Well, here is a matrix A, here is a vector v1, here is a vector v2. If we consider the norm of v1, Euclidean norm, that's root 2. Now, this matrix A times this vector returns 1, 1. And it has, as its norm, root 2, and so we have preservation of the norm. Here's a vector v2. Its norm is 5 root 26, and a little bit more computationally intensive. A times this vector is 11, 23, and its norm is 5 root 26. In fact, a rotation matrix would preserve the norm. And then the last question we could ask is, can a matrix preserve direction? Now, you got to be careful about the word direction, and we'll talk about that soon. So the question is captured by the equation. Ax, or that's the transformation on x, is a multiple of x. So the product Ax is collinear with x, lies along that line, that direction, could be a subspace. So when I say direction, I would put quotes around that. Okay, here's a matrix A. Here is a vector v1. This matrix times this vector is 4, 4, or 4 times the original vector. So they would be the multiplier, lambda would be 4. Stretch factor. Vector is x, 1, 1. Here's another vector, minus 1, 1, 1. Product of A times that vector is -6, 6. If I factor out the 6, it's -1, 1. So it's a multiplication, a stretch of this vector x by the factor 6. So this turns out to be the most useful extension of the question fixed point. It is a search for invariant subspaces. And that's the notion of the eigenvalue eigenvector pairing that we want to explore. So, what is an eigenpair? Well, here's a graphic demonstration of what we have just observed. Ax equals a multiple of x. The red vector is a unit vector, lies inside a unit circle. The black vector is this matrix A times that unit vector. Now this slider controls the unit vector. I've used the angle theta to represent the direction of that unit vector. Now in this configuration, the black vector, which is Ax, is collinear with the unit vector, that red vector, and the norm of Ax is 4. So the stretch factor is 4. If we change the angle, we see that the two vectors no longer line up, but for this angle, they again line up, but now the stretch factor is 6. So you can have a graphical visual representation of what we mean by an invariant subspace. And that's the reason why we have to be careful about that word direction, because if we keep changing the angle, keep increasing the angle, we again obtain this collinearity. And this direction is actually the negation of the direction that we first had. The angle was 45 degrees, and this is 225, so a difference of 180. Okay, so it is this whole line that remains invariant under the action of A, and that's why we talk about an invariant subspace. And if we keep going, it will come around to here. We see that again the stretch factor is 6, and this whole line is an invariant subspace. So now let's start thinking in terms of computing these eigenpairs, computing the eigenvalue eigenvector pair. So here I have installed the student linear algebra package, defined a matrix A and an arbitrary vector x, and in order for some of the context menu things I want to illustrate to work, I will initialize as I've just done. Okay, so how would one find an eigenpair directly in Maple? So here's the name of the matrix A, and then control equal echoes the content of that symbol, and a right click, go down to student linear algebra, eigenvalues, etc., and there are these two choices, eigenvalues, eigenvectors. If you make the choice of eigenvalues, you will get the two eigenvalues, which we saw were 4 and 6. If you make the choice eigenvectors, then the return is this pair of items. This is a vector. The vector contains the two eigenvalues. This is a matrix whose columns are the two eigenvectors. So the first one is connected to the first column. The second eigenvalue is connected to the second column. Now if you again use the context menu to select just this matrix, and for that one would use select element, select for example 2, so then selecting again this matrix using the context menu, there is the option to split this matrix into a list of column vectors, and this is given the name x, so that the first x would be this vector and the second x would be that vector. And there's one caution that I would issue here. The underlying command that Maple uses to obtain these results does not have a canonical ordering. So executing this at a later time may change the order. It may be 4, 6, and in which case these two vectors would switch places, and so the first x would then be this 1, 1, and the second x would be that negative 1, 1. That's what this comment down here says. Okay, so for a 2 by 2, one could get at these computations and this idea by saying ax and x should have an angle of 0, or it could be 180, could have an angle of 0 between them. So here I've put ax and x. If you use the context menu and go down to student linear algebra, there is a vector angle option. This would be the expression for the angle between these two vectors. Well, I deliberately set it equal to 0, but would not have to set it equal to 0 because Maple, when it applies the solve command, will make that assumption. And then I ask for a solution for one of these two variables, and I say solve for a, and I get these two solutions back, a equals b and a equals negative b. Well, what does that say for the vector x? Well, here's the vector x. Do a control equal, which is what this is equivalent to, and select evaluate at a point, and I set a and b equal to the same thing, and I have set it equal to 1, so I get 1, 1, and I'll call that v1. And if I set a equal to negative b and let b be 1, then a will be negative 1, and I'll call that vector v2. So if I have these two vectors, I can infer the eigenvalues by looking at the product av1. It's 4, 4. That's 4 times that the stretch factor is 4 times this vector 1, 1. And if I look at av2, the stretch factor is 6. 6 times the vector negative 1, 1. Now, another way to think of this is collinearity. We want ax to be collinear with x. It's not equal, it's collinear, so it's a multiple of x. So here is the pair, the sequence ax and lambda x. So this is the vector ax, this is the vector lambda x. I want these to be collinear. So these two are equated with the equate command in the context menu, and I get this pair of equations. And since I'm going to refer to them more than once, I'm going to call this list of equations E. So here we have 2 equations in 3 unknowns. There are the variables a and b. They constitute the vector x and this parameter lambda. How can we think about this? Well, here's a graphical way to think about this. I'm going to generate this graphic. This slider controls the value of lambda. And what you see are the equations of the lines that these 2 represent. You'll notice that they intersect at the origin because they're homogeneous. If you bring the a over to the to the left and the b over to the left, you'd have 0 on the right. So the equations are homogeneous. They intersect at the origin. A and b are 0 for this value of lambda. And they are 0 for all of these values of lambda. But lo and behold, when lambda equals 4, the two lines coincide. And there's only one line, which means that there are an infinite number of AB pairs, so that you are not restricted to the 0 solution, AB equals 0, that you would get for this value of lambda. And if we increase the value of lambda right here, when it is 6, the two lines are again coincident. And so there are an infinite number of solutions, not just the 0 solution. So graphically, you can see what control lambda has on the solution of this pair of equations. Well, suppose you just set out to solve that pair of equations. So it's ax equals lambda x. That's the pair of equations. Ask Maple to eliminate lambda. So it says, well, lambda has to be this, and the result is b squared minus a squared equals 0. Maple doesn't put the equals 0. If you then solve for example, a, this equation would give you a equals b and a equals negative b. Okay, so we know what the implications of those two solutions are. You get the vector 1, 1 and negative 1, 1. So keep thinking about this. Ax equals lambda x. That represents two equations. There are two unknowns, a and b, and you have this parameter lambda. What would be really wonderful if you could do it, because you could do it for inhomogeneous equations, nonlinear equations, you could get a and b as functions of lambda, and then you could see what effect lambda has on a and b. How close can we come to that? Well, here is a display of what we would like to determine. If lambda is 4, we saw that a has to equal b, in which case the vector x is a multiple of 1, 1. If lambda is 6, a has to be negative b, so the vector x is a multiple of negative 1, 1. Anything else forces a and b to be 0, and so the vector x is 0. So this is going to be hard to express in a functional relationship. This is going to be difficult to have with simple expressions. But how close can we come to it? So the first equation of the two in that list E is this. And if we isolate B, we have this. And if we substitute this into the second equation, we get this. If you bring everything to the left-hand side and simplify, you have this equation. Now, from this equation, you can see you're not going to solve for A. If lambda is 4 or lambda is 6, this equation does not determine A. Any other values of lambda, A is 0. So let's go back to this equation now. If you evaluate with lambda equals 4, well, you can see what's going to happen here. You're going to have negative 4 plus 5. B equals A. And if you evaluate with lambda equals 6, you're going to have negative 6 plus 5. You're going to have negative 1, so B is minus A. And so it is not going to be a simple task to to obtain A equals A of lambda, B equals B of lambda, but these are the issues behind that set of equations. Now, clearly, for somebody who's gone through enough linear algebra to understand dependence, independence, rank, all that kind of stuff, one goes at this more directly. But it's building that insight that we're trying to get to. Okay, typical textbook will write this equation, ax equals lambda x, as ax minus lambda x equals 0, and then factors the x out, and this a minus lambda I then becomes a source of great mystery. So let's take a look at what that looks like. A minus lambda I, there's your a, there's the lambda, there's the I, and lambda will multiply this one here, and lambda will multiply this one here, and so you will subtract lambda from the diagonal elements. And this then represents homogeneous equations. Can we get to that in Maple? Can we see that in Maple? So here's that set of equations. You can use the context menu to put this into matrix vector form, and the matrix vector form of this set of equations is this matrix and the 0 vector. So that's the right hand side. Right hand side is 0. This is called the characteristic matrix. And since you are solving a set of homogeneous equations, then you are looking for the null space of a minus lambda I. So when lambda is 4, you can write a minus 4. You don't have to type something for I. Maple will correctly form the matrix a minus lambda I if you just put 4 here. And what you're looking for is the null space, a generator of the null space. So that's the vector 1, 1. That's the eigenvector. And if lambda is 6, then the null space of this matrix is generated by the basis vector negative 1, 1, eigenvector. And finally, you get down to the computations that typically the textbook that the student is learning from will advocate, and it's useful to see in Maple what some of these steps are. So equations are homogeneous, and the statement that the student is bombarded with is the solution for x will be the 0 vector unless the determinant of a minus lambda I is 0. And that's the connection that we've been trying to make, but without having to make that statement. Okay, so the polynomial, which is the determinant of a minus lambda I, is the characteristic polynomial. Its zeros are the eigenvalues. That is the gist of what the textbook tries to tell the student. Okay, so let's see if we can do this in Maple. So here's a minus lambda I. Now I have explicitly put in the matrix representing the identity. And the reason is lambda is a symbol. So Maple doesn't know what this product represents. It doesn't know it's a scalar times a matrix because it doesn't know anything about lambda. And so you have to put in the matrix in that case. When this was a 4 or this was a 6, it was clear to Maple what that subtraction had to mean. Okay, so here is a minus lambda I. One gets its determinant. That is the characteristic polynomial. You can hit that with solve because Maple assumes you may set this equal to 0. And the solutions are 4 and 6. So the eigenvalues are 4 and 6. Those are the two numbers that lead to non-zero solutions of a minus or ax equals lambda x. Okay. You want to get the characteristic polynomial directly, get it from the context menu. Okay, and this is how you could get it from the context menu directly. If you have the eigenvalues and you want to determine the eigenvectors, this is the computation that you see in the typical textbook. You go back to a minus lambda I, which we can shorten in Maple as a minus 4. You get this matrix, but you're solving equations, so you row reduce this. So this is the row reduced form. And what the student often forgets is that that matrix, even the row reduced form, is multiplying a vector whose components are a and b. And so this first row represents the equation a minus b equals 0, which means a equals b, which means the two components of the vector are equal. Use the letter a, factor it out, and you get the generating vector 1, 1. And so you could call 1, 1 the eigenvector or any multiple of 1, 1. And you do the same thing for lambda equals 6. So a minus 6 gives you this matrix, and you row reduce. And what the student has to see is that that's representing a set of equations. So here are the AB multiplying or being multiplied by this matrix. So 1, 1 times that is a plus b. So a plus b equals 0. A equals negative b. So for a, you put in negative b. For b, you put in itself. You factor out the b, and you get negative 1, 1. So what would this all look like if we up the dimension by even 1? So here's a three-dimensional example. Again, I do a restart so that everything is, all the letters A and X are unassigned. And here is the student linear algebra package inserted. Here's a matrix A and an arbitrary vector X with components ABC. What are the eigenpairs? So you type the name A, you do a control equal, it echoes the contents, you right click, right, eigenvectors. Here is a vector of eigenvalues. The columns of this matrix are the corresponding eigenvectors. Now if we grab just that matrix and split it into columns, you will see these three eigenvectors. Now if you're working with pencil and paper, you might write this as 1 and this as 2, just to avoid the fraction. Now, can you get at this from the notion of collinearity? Well, in 3 dimensions, you have one extra tool at your disposal. AX is a vector. You want it to be collinear with X. If the cross product of these two vectors is 0, is the 0 vector, then AX and X are collinear. Okay, here is AX cross X. That's what this vector is. For this to be the 0 vector, all 3 of these expressions, component, 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 have to be 0. So I convert this to a list. Now there's first comma, there's the second comma. So there are 3 expressions. We would like each of those expressions to be set equal to 0, but the solve command doesn't really force you to put the equal 0. And then we ask for a solution. And Maple comes back with 3 solutions. ABC, ABC, ABC. So this is a sequence of 3 sets of equations that define ABC, and I call that S. So what vectors do these solutions represent? S1, here are the three equations, S2 to three equations, S3 to three equations. And I do a substitute into the vector x. And I get a0a, and I factor out the a, or evaluate at a point and set a equals 1, 101. I'll call that v1. Then I do the same thing with the second solution. Substitute it into x, and I get a, 2a, and 0. I can set a equals 1, which is equivalent to factoring out the a, and I get 1, 2, 0, rather than the 1/2 1 that Maple got earlier. Call that v2. And then the third solution, I get a, factor out the a, set it equal to 1, I get 1, 1, 1. I'll call that v3. And if I want to infer the eigenvalues from the eigenvectors, I can look at a v1, remembering that this is v1, and it comes back as 101. So the multiplier, or stretch factor, or eigenvalue is 1. If I look at AV2, V2 being 1, 2, this comes back as 2, 4, so the multiplier had to be 2. And if I look at AV3, and V3 is 1, 1, 1, and AV3 is 3, 3, 3, clearly the multiplier was 3, so the eigenvalue is 3. What about from the perspective of proportionality? So look at the equations contained in ax equals lambda x. So this is ax, right there, there is ax, and here is lambda x. You would like to see if these two vectors can be equal. So you equate like components with the equate option, and you now have 1, 2, 3 equations in 4 unknowns. A, B, C are the variables. Lambda is the parameter. So again, I call this E. And I'd like to do a graphical exploration here. So what these double-ended arrows represent are the lines of intersection of planes taken pairwise. So if I were to graph this equation, I would have a plane, but it would be parametrized by the value of lambda, so the plane would move around depending on this value of lambda, but the plane passes through the origin. Same thing for the other two equations, they represent planes. So I look at the intersection of the first and the second. Then I look at the intersection of the first and the third. Then I look at the intersection of the second and the third. So there are going to be 3 lines of intersection. And those lines are controlled by the value of lambda, right? Those lines will move around depending on the value of lambda. What I'm looking for here are values of lambda for which those lines are coincident, which means that all 3 planes have a common line of intersection. And so lambda equals 1 appears to be one of those values. And lambda equals 2 appears to be a second value of lambda for which those 3 planes have a common line of intersection. And then if lambda equals 3, there is a third value of lambda for which those 3 planes have a common line of intersection. So these are planes through the origin. If lambda is not one of these 3 numbers, 1, 2, or 3, then the only intersection common here is the origin 0, 0, 0, and A, B, and C are 0, and the vector x is 0, which we reject as an eigenvector because it's just not interesting. analytically, here are those three equations. So eliminate lambda, and there are now two equations in ABC, two equations in three unknowns. So grab this set of equations and solve for B and C in terms of A. So here's one solution, here's a second solution, here's a third solution. I'm going to call that sequence of solutions Q. Here are the three solutions, Q1, Q2, Q3. If I substitute into the vector X, I get A, 0, A. I factor out the A by setting it equal to 1, 101. Do the same thing here for the second solution. I get 1, 2, 0. And for the third solution, I get 1, 1, 1. So this is V1, V2, V3. If you look at the eigenvectors as members of a null space, so here you look at A minus 1, here's A minus 2, here's A minus 3. You ask for the null space, generator of the null space, 101. Generator of the null space, here Maple uses 1/2 1, which is a generator. Any multiple of that generates the null space, so you could use 1, 2, 0, and here for lambda equals 3, the generator of the null space is 1, 1, 1. From first principles, this is what the student is shown to do in his textbook. So A minus lambda I, again, lambda at this point is a symbol. You must put the matrix representing the identity as a multiplier so that Maple knows what to make of this product. And so you see that lambda is subtracted along the main diagonal. For these three planes to have non-zero solutions or intersection, they have to be coincidence. These have to be linearly dependent. The determinant of this matrix has to be 0. So if you look here, Maple provides the determinant and the roots. Remember, you don't have to say equals 0 in Maple when you use the solve command, 1, 2, and 3. Clearly, one can get the characteristic polynomial directly. There is a characteristic polynomial option. The difference here is that Maple will factor out a -1. Here, the determinant is calculated, has the negative in front of the lambda cubed, and here Maple resolves that by making the coefficient positive. But these are equal to 0, so it doesn't matter. I mean, you're going to set them equal to 0. Okay, so then you have obtained the eigenvalues. Can you infer the eigenvectors? And as we did before, you look at A minus 1i, A minus 2i, A minus 3i. This is the resulting matrix. You row reduce that. And remember, this represents a set of equations. You have an ABC multiplying this row-reduced matrix. There are now two equations here. A minus C equals 0, B equals 0. So there's the B equals 0, and the A and the C are equal. So if you factor out the A, you get 101. Well, A minus 2, again, you row reduce, and you have representation of a set of equations, homogeneous equations. So you get A minus B over 2 equals 0, and C equals 0. So there's your C equals 0. A is B over 2. So B is 2A, A is 1A. You factor out the A, you get 1, 2, 1. And in the third case, you get A minus C, B minus C. Both of those are equal to 0. So A and C are equal, so I use the letter C. B and C are equal, so I again use the letter C. And if I factor out the c, I get 1, 1, 1. Well, unfortunately, the situation can get complicated. There are things like repeated eigenvalues. So here's a matrix. It has the following for its eigenpairs. There's an eigenvalue of 1 with eigenvector 1, 3, 0. There is an eigenvalue of 2 for which there are 2 eigenvectors. So now let's study this new situation here where one eigenvalue gives rise to 2 eigenvectors. So let's take a linear combination of these 2 eigenvectors. Okay, that's the vector ABA. Now, what happens if I multiply that vector, that linear combination vector, by A? I get 2 times ABA. In other words, any vector in the span of these 2 fellows here, 101 and 010, any vector in that span behaves like an eigenvector with eigenvalue 2. Now here's a picture. So this plane is the plane spanned by these 2 vectors, and this line is the line along which this eigenvector lies. So there's a glimpse of what can happen if you have a repeated eigenvalue. But it gets even worse, unfortunately. You can have the deficient case. Here's an example of the deficient case. Here's a matrix that has only the eigenpair 2 with this eigenvector. Oh. So there's only one invariant subspace. Here, there were 2 invariant subspaces, one of which was 2-dimensional and one of which was 1-dimensional. And that's the algebra that lurks behind this investigation of eigenvalues, eigenvectors, and by having some concrete realizations and some pictures, I think it just makes it so much easier for the student to comprehend what's going on. Now here is a matrix Q, which if used in the form Q inverse AQ will put A into its so-called Jordan form. Well, that's another big mystery, Jordan form. Now, this first column is a multiple of this one eigenvector. These other 2 columns are called generalized eigenvectors. How does one determine all of this, the generalized eigenvectors and the matrix Q and so forth? Well, if somehow or other you can find this third column, the second column will be A minus 2i times the third column. And the first column will be A minus 2i times the second column. So you start from the third column, you can then get the second column, you can get the first column. But how do you get this first column? Well, look at the null spaces of A minus lambda I. So this would be A minus 2i to the k. When k is 1, the null space would be called M1. When k is 2, the null space would be called M2. And for k equals 3, the null space would be called M3. And it turns out that these null spaces fit inside each other. In this example, M3 would be the whole space. This would be the eigenspace for the one eigenvector, and then this is in between. So let's look at A minus 2, A minus 2 squared, and A minus 2 cubed, the I in this instance, Maple will let you leave out. So you get a null space, get a null space, get a null space. Now, for the cube, you're going to get the whole space, so you get ijk, basis for the whole space. Now here is a null space for a two-dimensional null space. Here's the eigenspace from the single eigenvector. Now this is a diagram that represents how M3 contains M2, which in turn contains M1. There is a basis for M1. B2 must lie in M2, but not in M1. This must be distinct from M1. B3 must lie in M3 and not be in M2. And this is the one you have to find first. If you can find this one first, you can get this one and you can get that one. Time for another picture. What does this look like? This line is the direction of the basis for M1. It must lie inside M2. Now M2 is going to be a plane because it has two generators. And these are the two generators. The red vector is a vector not in M2. So it's not in the plane. Now the easiest vector to get that's not in the plane spanned by B1 and B2 would be to take the normal to that plane. That would be a choice for B3. So, if we take the cross product of the two null vectors that give us M2, we will get this vector. And we can take that as B3. And if we take the product of B3 with A minus 2i, we will get this vector. And if we take the product of this vector with A minus 2i, we will get this vector. And if you have a very good memory, you will recall that those are the three columns of this matrix I called Q. And if you draw another picture, you'll see this line is the line along which B1 lies. Now, that vector in blue and this gold vector, it lies in the plane spanned by these two null vectors. But these we throw out. The two green ones we throw out. And this vector and this vector constitute a basis for M2. This goal vector is not in M1, but it is in M2. And so those two vectors are appropriate. And the red vector is not in the plane. So here is a glimpse of how Maple could be used to make a whole lot of this linear algebra around the question of eigenvalues and eigenvectors and even generalized eigenvectors a little bit more transparent. And I will tell you an anecdote. After I got out of undergraduate school, I went to New York University, Courant Institute, and I had a course in linear algebra taught by Louis Nierenberg. And in the lesson on Jordan decomposition theorem, he was using colored chalk to represent these vectors as I've used colors here. And he didn't have very many different colors. And when he ran out of colors, he turned to the class and said, well, you know what I mean. Well, I didn't know what he meant. And it wasn't until way later when I had tools like Maple that I could begin to visualize and make concrete what this very abstract stuff would otherwise be.